The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are two different classes that may be participating. May be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmayo@ybcc.edu and I will respond as soon as I can. All right, so today we start the last chapter that we're going to be covering this quarter, chapter 11. And after some introductory material, we'll take a look at section 11.3. But before we do that, I want to review some properties dealing with exponents. For instance, if I have 2 to the 1 power, that's the same thing as just 2. If there's no exponent written, the implied exponent is a 1. If I have 2 to the 2 power, that's 4. 2 to the 3 power, that's 8, etc. But going the other direction, what's 2 to the 0 power? Well, any number other than 0 raised to the 0 power is 1. What about negative exponents? 2 to the negative 1 power is like 1 over 2 to the positive 1 power, or 1/2. 2 to the negative 2 power is like 1 over 2 to the positive 2 power, which is 1 over 1, which is 1 over 4, etc. Before we go on, do you have any questions about dealing with exponents of this nature? All right, then we're going to go to a different screen because we're going to be doing some graphing. Let's see here. All right. Can everyone see my graphing screen, hopefully?
Yes.
Thank you. Okay, let's say we have y equals 2x. That's a linear equation, and the graph would be a straight line. Let's say we have y equals x squared. That's a quadratic equation, and the graph would be a parabola. Okay, now let's undo all of that. Today, we're going to look at what is called an exponential equation, the form of which a basic one would be y equals 2 raised to the x power. So the variable is not the base, it's the exponent. Well, as I said in the past, when I'm starting with a new function and just kind of exploring it, I like to start with x values going from -3 to +3. That doesn't mean that I stop there, but that's where I'm going to start. So let's take a look at what happens when we find these ordered pairs. If x is -3, then y equals 2 to the -3 power, which would be 1 over 2 to the +3 power, or 1 over 8. If x is -2, y equals 2 to the -2 power, which is 1 over 2 to the +2 power, or 1 over 4, 1/4. If x is -1, y equals 2 to the -1 power, which is 1 over 2 to the +1 power, or just 1 over 2, or 1/2. If x is 0, y equals 2 to the 0 power, which is just 1. If x is 1, y equals 2 to the 1 power, which is 2. If x is 2, y equals 2 squared, which is 4. And finally, if x is 3, y equals 2 to the 3rd power, which is 8. Any question about how I got any of those values? All right, let's plot those numbers. Let's see. If x is -3, y is 1/8. That's about there. About. When x is -2, y is 1/4. When x is -1, we're up to 1/2. When x is 0, y is 1. When x is 1, y is 2. When x is 2, y is 4. When x is 3, y is 8. Okay. Now, that's obviously not linear. It kind of looks like half of a parabola, but as we'll see here in a minute, it doesn't completely look like a parabola. Let's see. I'm going to see if I've got a curve here that can graph that. Doesn't look like it. I'm just going to have to freehand it here. So, and over here. Now, what's happening to the y values as x increases by 1? The y values are doubling. What if x was 4? Well, y would be 16. If x was 5, y would be 32, etc. So to the right, as this thing goes to the right, it goes up more and more rapidly. But how about to the left? What if x is -4? That would be 1/16. -5, 1/32. -6, 1/64. So going to the left, this thing is getting closer and closer to the x-axis, but it never touches or crosses the x-axis. You just keep cutting. Let's see here. 1/16, 1/32, 1/64, 1/128, 1/256, 1 bigger and bigger and bigger, but 1 something is never going to be 0. It can get awfully close. Any questions about this graph before we look at another example? Okay, let's get rid of this.
I actually have a question.
Yes, Abel.
How would this be written in, what was it? Notation? Something notation?
Function notation?
I think like -infinity over -infinity, comma.
Oh, interval notation.
Yeah.
So how is what?
How would this be written in interval notation?
Okay, okay. Let's talk about that. Let me finish erasing this and we'll get to that. So let's talk about the domain and the range. I was going to get to that eventually, but we can go ahead and look at it right now. Well, can you see that the domain is all real numbers because this graph continues to the left? This graph, as it's going up, continues to the right. So the domain would be from -infinity to +infinity. However, the range, since the graph never touches the x-axis or goes below it, the range would be greater than 0. Okay? So the domain is all real numbers, but the range, the y values are just greater than 0. Is that what you were asking about?
Yeah, that's
okay.
What I was asking. Okay. That's what I was asking.
While we're at it, let's also look, where is the y-intercept? It's at 0, 1. X-intercepts, there are none. Okay. We also say that this function, it is a function, this function, see, this function increases over its entire domain. Entire, can't spell there. See, it's entire IN or EN? I don't know. Anyway.
It's EN.
It's EN. Okay, great. That's why I'm not teaching spelling vocabulary. So going from left to right, as x increases, y increases. Okay, so we say it increases over its entire domain. All right, I want to go back now.
Yeah.
Yes.
Can you, how did you find the y-intercept with just, oh, that's the y, oh, and then you flip it? Or is that, what's the, is the vertex the same as the y? I thought it was the x is the same as the y.
Okay, you're stuck in chapter 10. There is no
Yes.
vertex. There is no
Oh,
vertex
okay.
here. This is not a
Oh.
parabola.
Yeah. Oh, yeah. So,
What?
okay. Yeah. Okay. I
You
got
sure?
it.
All right. All right.
Yeah.
Yeah. The right hand, it kind of looks like a parabola, but it's not. Okay.
Yeah. I just wasn't. Yes. Yeah.
Okay. That's just fine. All right. Now, what I want to do now is take a look at the graph of y equals 3 to the x. So now we're going to change the base from a 2 to a 3. So when x is -3, y equals 3 to the -3 power, which is 1 over 3 to the +3 power, which is 1/27. When x is -2, y equals 3 to the -2 power, which is 1 over 3 squared, which is 1/9. When x is -1, y equals 3 to the -1 power, which is 1 over 3 to the 1, which is 1/3. When x is 0, y equals 3 to the 0 power, which is 1. When x is 1, y equals 3 to the 1, which is 3. When x is 2, y equals 3 squared, which is 9. When x is 3, y equals 3 cubed, which is 27. Oh, I want to go back for a minute to 2 to the x, and I want to look at one other thing I was going to point out. In a parabola, there was a vertex, and on the table we had matching y values. Here we don't have that, but look what we've got here. We've got reciprocal values. The same is true of this y equals 3 to the x. We've got 1/3 and 3, 1/9 and 9, 1/27 and 27. Okay, so y equals 2 to the x, it was doubling. What's it doing here?
It's tripling,
Tripling.
yes.
Tripling, right. So it's going to climb even faster, steeper. Okay, when x is -3, y is 1/27, 1/9, 1/3, 0, 1, 1/3, 2, 9, and then 3/27 is off the graph. But do you see to the right of the y-axis, the red line is below the black line, but then to the left, but to the right of the y-axis, it's climbing steeper and steeper. But notice the domain is all real numbers. The range is greater than 0. The y-intercept is at 0, 1, and it's increasing over its entire domain. Okay. Any questions there? Let's take a look at another graph. Let's see, let's go with green. We'll be environmentally friendly. Let's look at the graph of y equals 1/2 to the x. Okay,
Oh, I was actually going to ask a question about this. Thank you.
you're welcome. As they say, this is not my first rodeo. All right. Somebody says that anyway. Okay. Now, if x is -3, then y equals 1/2 to the -3 power, which would be the reciprocal, or 2 over 1 to the +3 power, which is just 2 to the 3rd power, or 8. If x is -2, y equals 1/2 to the -2 power, which is 2 over 1 to the 2 power, or 2 to the 2 power, which is 4. If x is -1, y equals 1/2 to the -1 power, which is 2 over 1 to the 1 power, which is 2 to the 1 power, or just 2. If x is 0, y equals 1/2 to the 0 power, which is 1. If x is 1, y equals 1/2 to the 1 power, which is 1/2. If x is 2, y equals 1/2 squared, which is 1/4. If x is 3, y equals 1/2 cubed, which is 1/8. Well, again, we have that reciprocal situation going on in the table, but now what's happening to the values? Are they doubling or tripling? What are they doing?
Decreasing by half.
Yeah, they're halving, so to speak, aren't they? Yeah. Okay, so let's see what that graph would look like. -3, 8, -2, 4, -1, 2, 1, 0, 1/2, 1/4, and 1/8. The domain is still all real numbers. The range is still greater than 0. The y-intercept is still at 0, 1, but now instead of it increasing, it's decreasing over its entire domain. Okay. Let's see here. I want to take a look at a couple more examples. Yeah, let's go back and do another red one. How about y equals 1 to the x? What would that look like? Well, let's see. If x is -3, 1 to the -3 power is 1 over 3 to the positive, 1 over 1 to the positive 3 power, which is 1 over 1, which is what? If x is -2, 1 to the -2 power is 1 over 1 to the 2 power, which is 1 over 1, which is 1. If x is -1, 1 to the -1 is 1 over 1 to the 1, which is 1 over 1, which is 1. If x is 0, 1 to the 0 power is 1, 1 to the 1 is 1, 1 squared is 1, and 1 cubed is 1.
I guess we've won the lottery.
There you go. So in this case, no matter what x is, y is 1. So we get that. Well, that doesn't look at all like the other functions, does it? No, it doesn't. So apparently the base right here can't equal 1, because when it does, it doesn't fit the pattern of what we call exponential functions. Okay, let's take a look at one other example. Let's say instead of y equals 2 to the x, we have y equals -2 to the x. First of all, I want to point out that's not the same as that. Here, that's 2 to the x with a negative sign in front. But here, the base inside is -2, okay? So they are different. Let's see here. Where's my mouse at? There we go. Okay. So now, let's see here. If x is -3, y equals -2 to the -3rd power, which is 1 over -2 to the positive 3rd power, which is 1 over -8, which is -1/8. Okay? If x is -2, y equals -2 the quantity to the -2 power, which is 1 over negative 2 to the positive 2 power, which is positive 1/4. If x is negative 1, y equals negative 2 to the negative 1 power, which is 1 over negative 2 to the 1 power, which is 1 over negative 2, which is negative 1/2. If x is 0, y equals negative 2 to the 0 power, which is 1. If x is 1, y equals negative 2 to the 1, which is negative 2. Y equals negative 2 to the 2 would be 4, and y equals negative 2 cubed would be negative 8. Well, what's happening to the y values there? What are they doing?
They decrease by half and then they increase by 2.
Well, yeah, and let's see here, this is blue. The sign's changing, isn't it?
Yes.
So if we were to graph that thing, let's see. When
It's gonna look
X-
weird.
It's gonna, not only is it gonna look weird, but it's not gonna happen. It doesn't work because you get a point here, a point there, a point back, you know, and it doesn't work. So where that gets us is, let's see here if I can find, having trouble finding my mouse this morning. Okay, or at least on the screen. We have the following situation. Y equals b to the x, okay? That is a basic exponential function or exponential equation where b is the base, okay? B has to be greater than 0. Remember, we had a negative base and that didn't work, but b cannot equal 1 because then it's just a constant function, a straight line, okay? If b is greater than 0 and less than 1, we get a decreasing function. If b is greater than 1, excuse me, we get an increasing function, okay? That's just kind of a general summary of what we're talking about. So the base has to be positive, greater than 0, but it can't equal 1 because then we get this thing that's flipping all over the place. If the base is between 0 and 1, it decreases over its entire domain. If the base is greater than 1, it increases over its entire domain. Okay? Now, let's do this. Let's see here. Let's go to the next page. And let's again look at y equals 2 to the x. X, y, negative 3, negative 2, negative 1, 0, 1, 2, 3. And this is 1/8, 1/4, 1/2, 1, 2, 4, 8. Okay. And the graph of that thing, let's see, looks something like that. Oops, I went too low. Okay. Now, what if I graphed y equals 2 to the x plus 4? So I added a constant. Think back to the quadratic or second degree equations. If I had y equals x squared, and then I had y equals x squared plus 4, didn't that move the graph up 4 units?
Yes.
Thank you. So what's this going to do? It's going to move this graph up 4 units. So let's see. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Etc. Etc. Okay. So you'd get a graph that would look kind of like that. What if it was y equals 2 to the x minus 3? What would that do?
It would lower by 3, right?
Good, good. Okay, now That's outside, which causes a vertical shift up or down. So what about this? Y equals 2 to the x plus 2. Now the plus 2 is part of the exponent. Think about what happened when we went inside the x squared with a parabola. We had something like that. It shifted it to the left 2 units, didn't it? That's what's going to happen here. So this plus 2 is inside by the variable, inside inverse. So a plus 2 is going to move the whole thing that way 2 units. Y equals 2 to the x minus 3, where the minus 3 is part of the exponent, would move it that way 3 units. What about this? Y equals negative 2 to the x. Now, that's not negative 2 to the x. It's negative 2 to the x. In other words, it's not the base is still a positive 2. Well, if this is y equals x squared, what did y equals negative x squared look like? It opened downward, didn't it? So this would look like that. Okay, it would flip it over. And my graphs are not accurate at all. They're just trying to give you the idea of what generally happens. So we've got those same kind of shifts upward or downward, to the right or to the left, flipping over, that we had with the quadratic or second degree equations. Okay, that's all I want to say about that right now. And I want to look at some other ideas. So let's see. Let's go back to the other screen. Okay. And okay. Now, what if I had y equals 2 times 3 to the x? Order of operations, is that the same thing as 6 to the x?
Yes.
Contra.
No.
No. You do the exponent before the regular
Oh.
multiplication. Yeah, good try, good try. It's Monday. Okay. So, for instance, where would the x, or no, not the x-intercept, where would the y-intercept be here? If x is 0, y would equal 2, wouldn't it? Because this would double whatever you got here. Does that make sense?
Yeah.
Mm-hmm.
Okay. Also, since the base is greater than 1, this thing is increasing, isn't it? So it's going to have a y-intercept of 2, and it's going to increase. Okay. Now, what if I had y equals 3 times 0.5 to the x power? Where is the y-intercept now?
Somewhere fun.
Somewhere fun. Where would it be? What's 0.5? What's 0.5 to the 0 power?
That'll be 1, right?
Right. So 3. I guess 3 is fun. But now, is this thing increasing or decreasing?
I'm not sure.
What's the base?
Positive
Yes.
and greater than 0.
Yes. But it's
So would
also
it be-
less.
Hmm.
Go ahead.
So it would be decreasing then, right?
Yes, because the base is between 0 and 1. So this thing's going to start at 3, but then it's going to go down. Okay.
Mm-hmm.
All right. Now, let's see here. Let me ask you this. F of n equals 650, 0.94 to the n power. Okay. What's the y-intercept or the f of n intercept for this function? So what's the y-intercept? It's actually in, tell you what, let's do this. Let's make it f of x equals 650.94 to the x. Okay. So what's the y-intercept?
That'll be 0, 650, right?
Yes,
If
because when x is 0, this is 1. 1 times 650 is 650. Does this thing increase or decrease?
decrease, right?
Okay, why?
Because it's less than 1.
The base is less than 1. Correct, correct. Okay. Let me ask you this. A equals 500 times 2/3 to the t power. Okay. This is a population of some substance. How much is there to start with at the beginning of time?
If we're starting at 0, it'll be, if we're starting with x being 0, it would be 1. Oh, wait, 500, right?
500. Is the population increasing or decreasing?
Looks like it's decreasing.
How do you know?
The base is less than 1.
Good. I think you're getting this. Okay. We're going to look at a special formula. This is called the formula for compound interest. And it looks like this. A equals P times a quantity 1 plus R over K to the KT power. Now, P is the principal, so the amount that's invested or the amount that you start with. R is the annual rate of interest. K is the number of compoundings per year. T is time in years. And A is the, I'm going to say, accumulated amount. See, that's not right. There's no L there. Accumulate. I told you I was a great speller. Actually, A spelling, because I could memorize things for about 10 minutes. And then after the test, don't ask me how to spell hippopotamus. Okay. So let's take a look at a problem involving compound interest. Okay. It says compound interest. An initial deposit of $10,000, so that's the principal, earns 8% interest, so that's the interest rate, which we're going to rewrite as a non-percent number, so 0.08, okay? Compounded quarterly, so the interest is compounded 4 times a year. How much will be in the account after 10 years? All right. Now, the idea of compound interest is where you make interest and the interest stays in the account. And so then the next year you've got interest on the interest, and the year after that, interest on the interest on the interest. But here it's compounded 4 times a year. So every quarter they put the interest in the account that you've earned, and then it starts to earn interest on that interest. The more often it's compounded, the better off you, the customer, are if you're collecting interest. All right. So what's this going to look like? A equals 10,000 times 1 plus 0.08 divided by 4 raised to the 4 times 10 power. Now, you can put all this into your calculator at once. If you're going to do that, you'd have to go 10,000, parentheses, 1 plus 0.08 divided by 4, close parentheses, that little power button, caret key, parentheses, 4 times 10, close parentheses, equals. Okay, now I'm going to do that. Let's see, 10,000, parentheses, 1 plus 0.08 divided by 4, close parentheses, raised to the power, parentheses, 4 times 10. When I do that, I get 22,080.39664. Okay, now, since we're dealing with money, we're going to round to the nearest cent. One column over, this would round up, so our final answer would be $22,080.40. Okay, let's go back for a minute. And let's say you don't want to put the whole thing in your calculator at once. Okay, for instance, this is 40, not a problem. Then the question is, does this come out nicely? Let's see, well, 0.08 divided by 4, oh, that's 0.2. So I could rewrite it as 10,000, 1 plus 0.0 be 1.02 raised to the 40th power. Okay, now I could put that into my calculator. The thing you got to be careful of, though, if this, for instance, does not come out to a nice number like 0.02, do not round it off. If it doesn't come out to a nice number, you better stick with the original amount, because if you round off before the end, it's going to skew your answer. Okay, you rarely want to round off before the end of a problem unless it tells you to. So be careful with that. Okay, now this says comparing interest rates. How much more interest could $1,000 earn in 5 years, compounded quarterly, if the annual interest rate were 5.5% instead of 5%? Okay, so in the first scenario, we're going to invest $1,000. The annual rate is 5%. It's compounded quarterly, and it's left there for 5 years. Okay. In the second scenario, we're going to have the same amount of money, but the interest rate is 5.5%, which would be 0.055. Same amount of compoundings per year, same time. So the question is, by raising the interest rate 0.5%, how much more money do we make? Yeah, all right. So first scenario, A equals 1,000. 1 plus 0.05 over 4 raised to the 4 times 5 power. Okay, so let's see what I get. 1,000, parentheses, 1 plus 0.05 divided by 4, close it up, raised to the power, parentheses, 4 times 5. I get 1282.037, which is going to round up. Okay, so $1,282.04. Now, second scenario, this is going to be 0.055 over 4 to the 4 times 5 power. 1,000, parentheses, 1 plus 0.055 divided by 4, close parentheses, raised to the power 4 times 5, and I get 1314.066, which would round up to that. Let's see, if I take 1314.07 minus 1282.04, $32.03. So $1,000 compounded 4 times a year, interest rate for 5 years. By adding a 0.5% interest rate, you get $32.03 more. And you might not think that's much, but let's say you've got 2 banks that you could put your savings in. One of them's paying 5%, one of them's paying 5.5%. Why not invest in a better interest rate? Anyway, any questions on that?
I don't think so.
Okay. Let's see here. Okay. This problem says population growth. The population of North Rivers is decreasing. That's odd. It said population growth, but it's decreasing exponentially according to the formula P equals 3745 times 0.93 to the T power, where T is measured in years from the present date. Find the population in 6 years, 9 months. So time equals 6 years, 9 months. First of all, at the beginning of this problem, at the beginning of time for this problem, what's the population of, was it North Rivers? Yeah, what's the starting population?
3,745, right?
Good. Okay, now be careful. Be careful. Is the population increasing or decreasing?
They said decreasing.
They said it, but forget what they said. Look at the function. Is it
should
increasing?
be decreasing due to the base being less than 1, right?
Good. Now be very careful. By what percentage is the population decreasing per year?
That's a little trickier.
This is the Jeopardy bonus question. By what percent is the population decreasing per year?
It's
Okay, I'll give you the answer. It's 7%. Where did I get that? All right. Since the base is 0.93, that means that every time T increases by 1, so another year goes by, we take whatever amount we've got and we multiply it by 0.93, which means you now have 93% of what you had before.
I see.
So you're losing 7%. See it?
I see.
Okay.
Say that again.
What's that?
Will you say that again?
Yes. Okay. So the base is 0.93. So as time goes on, as T increases by 1, we multiply whatever we have by 0.93, by another 0.93. Okay.
Okay. Yeah.
0.93 is like 93%. So let's say you have a population and you multiply it by 93%. What did you lose? You lost 7%.
7%. Okay, got it.
Yeah. Okay. Good. 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 All right. Oh, they want to know what the population will be 6 years and 9 months later. So be careful. How would you convert 6 years, 9 months into a single number that's written in terms of years?
6.75, right?
Good job. Because 9 months 9/12 of a year, 3/4 or 0.75. So let's see what we get if we raise that to the 6.75 power. Is it going to be bigger or smaller than than our starting value?
It's going to be significantly smaller, right?
Right, smaller. Good. And I'm coming up with 2294.6. So rounding to the nearest person, we would have 2,295 people left. Okay. All right, let's do one other problem. Let's say that $1 has been invested on July 4th, 1776. It's that silver dollar that George Washington threw across the Potomac, or whatever that story is. Okay. At 5% interest compounded annually, what would it be worth on July 4th, 2076? Okay.
We're not accounting for inflation, right?
Correct. We're not accounting for inflation. Don't make it too complicated. All right. So principal is $1. The rate is 5%. Number of compoundings is 1 because it says annually. Time is what? 2? No. Let's see. From 1776 to 2076 would be what? 3? Is that 300 years? Yeah.
I think so.
Okay. So A equals 1 times 1 plus 0.05 over 1, the 1 times 300. If I simplify this down, I get 1 times 1.05 to the 300th power, which is just 1.05 to the 300th power. 1.05 to the 300th power. Oops. 1.05 to the 300th power. And I'm getting 2,273,996.129. So $2,273,996.13. If we'd only invested $1 back then, if George Washington, instead of throwing that dollar across the Delaware, had put it in the bank, he'd be a millionaire. He'd also be dead, but that's irrelevant. All right. So for tonight, section 11.3, I'll be back this afternoon at 1:15 with an office hour. Should you have need of me, I will stop the